Please don't forget to like, subscribe, and comment. Thank you so much.
Join us at Like Learning School and experience a transformative education journey. Visit our website at www.likelearningschool.com or contact us at +2348085095144 to learn more and get started today.
That deformation of solids, Hooke's law and what have you. You can see where I am?
Yeah, I can.
Okay. Do you remember Hooke's law? That's from O level.
F equals to KE.
F equal to KE. What does F stand for?
Force.
K.
Constants.
Spring constant, and then E.
Extension.
Okay, that's the mathematical equation for Hooke's law. F equal to KE. F for load or force. K equal to spring constant. E for extension. But what does Hooke's law talk about? What does it really talk about?
Hooke's law states that the extension of the string is directly proportional to the force applied on it until we have reached its limits of proportionality.
Oh, okay. Yeah, you captured it well. Hooke's law states that extension is directly proportional to the applied force. That is beneath the elastic limit. Because above the elastic limit, it doesn't obey Hooke's law again. So, just a quick review. And please, I'm on the next page, so that I can just note this down. Hooke's law, beneath the elastic limit, extension is proportional to the applied force. Extension is proportional, or directly proportional if you like. Extension E is directly proportional. Some textbook can use X for extension. It doesn't matter. Proportional, directly proportional to the load or force, which is F. Okay, so mathematically, as we rightly said, F is equal to KE. Okay, so if obviously if we plot the graph of F against E or E against F, by the way, what the proper way, based on that definition, which one is the independent variable?
What did you say?
Based on this definition of Hooke's law, which one is the independent variable?
Independent variable.
Yes. Yeah, which one is the independent variable? Is it the extension or the force?
Oh, independent variable, the one that was like equal or force.
Independent, yes, is the force. Okay, dependent is the extension. Of course, K is a spring constant. And you know the unit of K will be, the SI unit should be SI unit of K should be, since it is force, okay, let me just make a solid formula. Or K is equal to F over E, isn't it?
Yeah.
So the unit of K should be Newton per meter. Okay, unit of K is Newton per meter because it's about force over length. All right. Okay. What I was trying to tell you is, if the independent variable is force, the proper way of plotting it, although the other way can be, you can also see it plotted in the other way. But the the reasonable way of plotting it, because the independent variable is usually on the x-axis. So force will be here in Newton, extension will be here in whatever unit you like, maybe meter. Okay, so beneath the elastic limit, as we said, extension is directly proportional to the resultant, to the force. So it's going to look like this. Are you on the Jamboard, please?
Yeah.
All right. And let me draw this again. Beneath the elastic limit is going to be like this. Now, once it goes beyond the elastic limit, it's no longer going to be proportional, so it will curve. This position we can call E is the limit of proportionality, or elastic limit. And you know, A to E is the elastic region. E to any position F is a plastic region. So A to E, you know, is elastic region, just from known to unknown. And E to F is the plastic region. So when you stretch a string and it is still within its elastic limit, and it can return to its original length after releasing the load, after letting the load off. But if once it enters the plastic region, it doesn't return fully to its original length after the load is removed. So we say that it has been permanently deformed. You know what I'm talking about?
Yeah.
Okay, of course, E is the limit of proportional elastic limit. So Hooke's law is obeyed within which region? From where to where is Hooke's law obeyed?
A to E.
A to E, okay. So what will be the slope? What will the slope give you?
The slope would be wait, what do you mean by this?
Yeah, gradient. What would the gradient give you?
The constant.
Of E. Remember, this is a graph of E against F. What would the gradient give you?
The constants.
Yeah, what will be the value? Slope is equal to, since it is E plotted against F, that's going to be E over F. And what would that be? I think that should be 1 over K, isn't it?
Yeah.
Do you agree? Let me write this one lower. This is, just hold on, let me put this here, F in Newton. The slope is going to give us 1 over E. Because 1 over K rather. Because K itself is F over E. So if the slope is E over F, because it is E rise over run. Rise is E, run is F. So E over F will now be 1 over K. That is if you plotted E against F. You know what I'm talking about?
Yeah.
All right. So Hooke's law states that beneath the elastic limit, extension E is directly proportional to the load or force. It is only proportional when it is beneath the elastic limit, but beyond it, it is no longer proportional. So the proportionality is between A to E. If you stretch it beyond the elastic limit, it doesn't return to its original length when released. So if it is stretched still within the elastic limit, the elastic region, it can return to its original length. All right, please, can you go to the previous page? I want to show you something so that we can move on from there. So a graph of F, or extension over F, as we have said, gives a slope of 1 over K. Remember, X stands for extension. We can as well call it extension against F. All of these are extensions against F. extension against F, or F against extension. So extension against F, the slope gives 1 over K, because it is rise that's rise over run, rise over run, which is E over F, that gives 1 over K. But if it is a graph of F over E, F over E, the slope gives directly K, spring constant. Now this is what I'm talking about. Let me zoom it in here properly so that we can see. You know, this initial graph we plotted is E over F, E against F, which gives 1 over K. But if we decide to plot a graph of F over F against E, like this, F here, E here, this one is going to give us, the slope will give us directly spring constant. So this is how it's going to look. But we need to notice something. When a graph of F is plotted against E, after or beyond the elastic limit, the graph will curve downwards like this. So if E is the elastic limit, it's going to curve downwards like this. Take note of the difference. F against E, this is the elastic region. The plastic region is going to curve downward. Compare it with a graph of E against F. A to E is the elastic region. E to F is curving upwards for the plastic region. That is for E against F, extension against load, extension against force. And you can see the difference when it is force against extension. So what I'm saying is, if we take the slope here, this particular one, where we plotted force against extension, the slope will give us rise, which is F, over run, which is E, and that is directly spring constant. Slope is F over E, which is a spring constant K. This gives a spring constant K. Unlike a graph of E against F, the slope or gradient gives E over F, which is 1 over spring constant. Okay. Oh, I should have called this a different name, so that let me call this P instead of F, so it doesn't confuse some of the things that we need to talk about. So A to E is the elastic region. When you stretch it and you remove the load, it will return to its original length. So it has not been permanently deformed. E to P is the plastic region. When you stretch it beyond the elastic region and you remove the load or the force, it will no longer return to its original length, because E is the elastic limit. Beyond the elastic limit, it doesn't obey Hooke's law again. Before the elastic limit or below the elastic limit, it obeys Hooke's law, where extension is directly proportional to force. So it forms a straight line that passes through the origin. Just like if you plot the graph of F against E, it will also produce a straight line that passes through the origin. And after the elastic limit, it curves, because E to P is the plastic region. Alright, but I want us to notice some important features of the graph. I want to review both so that we can compare. Let's see a graph of E plotted against E, F against extension. You see, when we take the slope gives us directly spring constant. And as you can see, the slope for the black one is bigger than the slope for the blue one. That means the spring constant of M, which is the black one, is bigger than the spring constant for Q, which is the blue one, because it is steeper. M is steeper, and the slope gives directly spring constant. Spring constant of M is bigger than spring constant of Q. But I need you to see the difference. When you plot E against F, the slope is not K, but it's 1 over K. So even though B is steeper than A, the black one here is steeper than the red one, the slope of A is actually, or what I mean is, yes, I said even though B is steeper than A, meaning that B has a higher slope than A, but the spring constant of A is bigger than the spring constant of B. The spring constant of A, the red one, is bigger than the spring constant of B, the black one. Reason being that it is the other way around. The graph is plotted the other way around. It is E against F instead of the normal F against E that we usually plot. I just want us to see how we can find the work done or the energy stored in a string. The work done or the energy stored in a string or in a spring within the region where it obeys Hooke's law is the same way we can calculate work done, force times distance moved in the direction of the force. And since we are going to use the average force, so we have half F times that distance. Now this time around, the distance is going to be the extension. So that's going to give us average force times the extension. Work done is force times distance. So it is the average force times the distance. Average in the sense that it started with a force of 0 and then it gets to another force. The force is not constant. So we need to use an average force. Initial force plus final force divided by 2. Or simply half F, because initial force is 0. Final force can have a value we can call F. 0 plus F divided by 2 give us the average. And 0 plus F divided by 2 is simply F over 2 or half F, which is the average force. Now times the distance, which is extension. That will give us half F times E. So that's the average work or the work done in a string, where F is the force, E is the extension. So half times force times the extension, which is basically area under the graph. Area under the graph of force against extension will give us the work done in stretching a spring or deforming a spring, or the energy stored in a spring that is stretched or squashed. That work done or energy is half times force times extension. Now we can take that further by, if we take that further, we'll be able to get this equation half Ke squared. Now how did we get that? We know that from Hooke's law, F is equal to Ke. You know, Hooke's law is F equal to Ke. Or F equal to Kx. K is the spring constant, E is the extension. So if F is equal to Ke from Hooke's law, and then we substitute Ke for F. Instead of F, we substitute it with Ke. The equation will change to half Ke squared. What I mean is, for this F, we change this F to Ke. This F is now substituted with Ke. So instead of half Fe, we're now going to have half Ke for F times E again. So half Ke then E, or half Ke times E, which will give us half Ke squared. So the energy stored in a spring or in a string is half Ke squared in terms of the spring constant, or half Fe squared, or half Fe in terms of the force and the extension, which is equal to half Ke squared is in terms of the spring constant K, and of course the extension. Now we can look at different ways we can analyze the spring constant. You know, a string can be connected in parallel or in series. This is what I mean. I'm going to draw a line here. Anyway, this is about a different topic which we'll look at later in another lesson. But for now, we're looking at stress and strain, or deformation of solids. Now, a string can be connected in series like this. I mean, you can have two strings in series. This is one string, then yet another string. I'm going to add this other string in green. So let me call the first string A, having a spring constant of K, and then I'm going to call the second string B, having a spring constant of B, or KB. The first string has a spring constant of Ka, the one in red. The second string has a spring constant of Kb, the one in green, connected in series. That's end to end. This is series. Or end to end, one end to another end. When strings are connected in series like this, the total spring constant, this total spring constant K total, is equal to 1 over a spring constant of 1 plus, actually this is how we should look at it. If you remember resistances connected in series and in parallel, it will give you an idea of what we're talking about, though in a reverse way. So 1 over the total spring constant, I'll call it 1 over K total, is equal to 1 over K1, that's Ka, plus 1 over Kb, 1 over Kb. You can recall where we normally do this in electricity. In fact, in electricity, you find this for parallel circuits. Incidentally, when strings are connected in series, this is how we find the total spring constant. which is like what we do when resistors are connected in parallel. In fact, this will give us product over sum. If you have only two springs, for only two springs, this is going to be product over sum. So that's for only two springs. If you have more than two, you have to apply this formula as it is. 1 over K total is equal to 1 over Ka. That's for one spring, plus 1 over Kb for the other spring, plus 1 over Kc for the other third spring, 1 over Kd for the fourth spring, as many strings as possible. But for only two springs, which I'm going to talk about now, for only two springs, for two springs in series, we can simply do product over sum. K total, this total spring constant is simply product divided by sum. Product divided by sum. In other words, the product of the spring constant divided by the sum of it, which in this case will be Ka times Kb over Ka plus Kb. Let me write it out in full. And that is only when we have two springs in place. So this will be Ka times Kb, Ka times Kb, or Ka-Kb divided by, okay, I think I would better use just the same color. Or, okay, let's go ahead with Ka times Kb divided by Ka plus Kb. Ka times Kb divided by slash Ka plus Kb. Okay, so Ka plus Kb. Ka, I think I zoom this thing to 200% to reveal it better. As for string in series, Ka plus Kb plus Kb that's product over sum in brackets. Let me write it better so that this will come out clearer. I said for two springs in series, the total spring constant, K total, is simply product over sum. That's only for two springs in series, which in this case is going to be Ka times Kb divided by Ka plus Kb. Plus Kb. Okay, that comes out better now. So plus with our bracket in place. Alright, so that's what we do for springs in series. And if you notice, when springs are connected in series, the total spring constant will always be smaller than the smallest of the spring constants. You can use an example to illustrate this. Assuming, just for your own illustration, you can use a spring constant of, say, 5 Newton per meter for Ka, and then the other one maybe 10 Newton per meter. By the time you calculate the total spring constant, which is Kt, whether you want to use this formula or you want to use this formula, product over sum, which is Ka Kb times Ka times Kb divided by Ka plus Kb, you will discover that the total spring constant, the total spring constant will always be smaller than any of the smallest, or it will be smaller than even the smallest spring constant. In other words, the spring will become less stiff. When you connect springs in series, it becomes less stiff because the spring constant gives an idea of the stiffness. The bigger the spring constant, the stiffer the spring. So if the total spring constant is going to be even smaller than the smallest one, it means that springs connected in series will produce a less stiff total spring, or less stiff effect, because the total spring constant will be smaller than even the individual spring constant, or the smallest of them. That's for spring connected in series. Spring connected in series, that's end to end. Now, springs can be connected in parallel. Let's illustrate that here. We can have springs connected in parallel. This one is easier, so we don't have much to do. The springs are connected in parallel like this. We have this first spring in red connected like this, and then another spring in green connected like this. In this case, they are connected in parallel, all supporting a load, both of them holding a load in place. The spring constant of this one is Ka, the one in red. The spring constant of the one in green is Kb. When connected in parallel like this, that's across each other, not end to end like in series. This is for parallel. Parallel is different from series. Parallel is this way, series is this way. Series is this way, parallel is this way. Series, they are connected end to end. One connected from the end of the other. This green one connected from the end of the red one. That's series, end to end. The parallel is across each other. The total spring constant for parallel, K total, is just the sum of each of them. So that will be Ka plus Kb. simple sum. And we can see that the total spring constant for springs connected in parallel, the total spring constant will be bigger than even the individual spring, because you have to add up the individual spring constant. So when springs are connected in parallel, the system becomes stiffer because it's a higher total spring constant. So in this case, system becomes stiffer. Higher K means or implies stiffer system. In stiffer, if K is higher, if the spring constant is higher, it means it is going to be stiffer. But here the spring constant is less, it's going to be less stiff. So this one is lower K, or I can call it lower K total, for lower K total, which implies less stiff. That's for series. Lower K total for series will be less stiff when in series. Higher K total for parallel, that means more stiff or stiffer. So this is the way it will be when these springs are connected in this way. In summary, in series end to end, the total spring constant is 1 over K total equal to 1 over Ka plus 1 over Kb plus 1 over Kc plus 1 over Kd, as the case may be. Or when there are only two springs, the total spring constant is simply product over sum, or Ka times Kb all over Ka plus Kb. That's for series. And that will produce a lower total spring constant, which means less stiff. But in parallel, for parallel, the total spring constant Kt is just the sum of the individual spring constant, and that will make it stiffer. So when they are arranged across each other, which is parallel, it will produce a stiffer system. Another concept we look at is stress, strain, and the Young modulus. For this graph of force against extension, the graph of force against extension, let me make it bigger. A graph of force against extension. We can modify the graph to obtain some other features. First of all, a quantity we call stress usually denoted by this symbol, is equal to force over cross-section, cross-sectional area. So stress is force over cross-sectional area. That means the unit of stress will be, since it is force over cross-sectional area, the unit will be Newton per meter squared, which is like the unit of pressure. So unit, because the unit of force is Newton, unit of cross-sectional area is meter squared. So the unit of stress is force over cross-sectional area, or force per Newton, or Newton per meter square. Unit is Newton per meter square. Unit of force is Newton, unit of cross-sectional area is meter square. So the unit of stress is Newton per meter square, because stress is force or normal force over cross-sectional area. That's the load divided by the cross-sectional area of the material. We have another quantity we call strain. Strain usually represented with this symbol, epsilon. Strain itself is equal to extension over original length. Extension over original length. We can call the original length L naught. By the way, extension itself is new length minus original length. You know, to check how much the thing has extended, you need to check the difference between the current length and the previous length. So new length minus original length is extension. You might want to say extension is new length L minus original length. So strain is new length minus original length all over original length. So we can define each of these. This stands for new length. L stands for new length. L naught stands for original length. So of course E is extension. E stands for extension. So looking at this, the strain is about centimeter over, or length over length, which means strain, which is about length divided by length, we have no unit because the units we cancel out. The unit of extension, SI unit is meter. The unit of original length, SI unit is meter. So the meter will cancel out the meter. So the strain has no unit. Strain is a unitless quantity, just like relative density and what have you. Strain is a unitless quantity. Has no unit because the units we cancel out. So the strain has no unit. Because the unit of extension is meter, SI unit, the unit of original length is meter, so they will all cancel out. So stress is force over cross-sectional area. Strain is extension over original length. The unit of stress is Newton per meter squared. Strain has no unit because the units cancel out. It's about length or meter and about meter. So they cancel out. Now, the cross-sectional area you can find out using relevant mensuration formulas. For a circular cross-section, a wire with a circular cross section, you can use pi r squared, to find the cross sectional area. So e.g. pi r squared for a circular cross sectional area, pi r squared, or pi d squared over 4 if the diameter is given. You can use that to find the cross sectional area of the wire, while the force will be the load. And for the force, we can multiply the mass in kilogram times g, where g is the gravitational field strength. Mass in kg, in kilogram, times g, because the force is the weight, so the mass times g will give us the weight. All right, so with these new quantities, stress and strain, we can modify this graph slightly. If we divide this, our initial force against extension, if the force is divided by cross-sectional area, if I do force over cross-sectional area, that will give me stress. Imagine it's giving me stress. And for this part, remember, force over cross-sectional area is stress. That's it. Force over cross-sectional area is stress. For this part, if I divide the extension, by the original length, that will give me strain. So a graph of force over cross-sectional area against extension over original length is a graph of stress against strain, and it will also produce a straight line that passes through the origin for the part where Hooke's law is obeyed, until the elastic limit E. For some materials, there will be a yield before it enters into some other regions, and then it snaps. So we can use this to find the highest stress possible, this part. This is what we call this position, which gives us the highest stress possible, the highest stress, because this part is stress. Let me label it. This is stress. Remember, this one is strain. So the highest stress possible is what we call the ultimate stress. So this produces the ultimate stress. This point is the region of the ultimate stress, which we can call D subject U, ultimate stress. Ultimate, or the maximum stress possible. The delta subscript U is the ultimate stress. Remember, during the elastic region, it obeys Hooke's law, so the graph is a straight line that passes through the origin. Within this region, which I can call O to E,
if the load is removed, it will return to its original length. Now it will, once it exceeds the elastic region and then it enters the plastic region, plasticity, this whole region is the plastic region. When the load or the force is removed, it will no longer return to its original length. So we say it has been permanently deformed. Now this is the highest stress possible. The value obtained at this peak is the highest stress, which we call the ultimate stress. We can analyze this further to obtain another quantity. If we take the slope of this graph, which I'm going to show like this, the slope is stress over strain. That's stress over strain divided by strain. And that slope gives a quantity we call Young modulus, E. E is a Young modulus. Young's modulus. So the slope of the graph of stress against strain, which is stress over strain, gives E, or the Young's modulus. We can look at the Young's modulus in a different way. Now, we already said that stress is force over cross-sectional area, and strain is extension over original length. And we have defined Young modulus to be equal to stress over strain divided by strain, stress over strain. That's for the Young modulus, stress over strain. Now, if we substitute this, we're going to have F over A for stress, because stress is F over A, divided by extension of original length for strain. So extension of original length for strain. Simplifying that further will give us this. Force times original length divided by cross-sectional area times extension. That will give us the Young's modulus. If we simplify this is what we're going to get. F over A divided by E over L naught will give us F times L naught over AE. Simple arithmetics. F over A divided by E over L will eventually give us FL naught over AE. And we know that F over E is a spring constant. So this will actually give us spring constant K times L naught over A, because F over E itself, F over E, force over extension, is a spring constant. Force over extension is a spring constant from Hooke's law. Hooke's law states that F is equal to KE. F is equal to KE. So K is equal to F over E. So F over E is a spring constant. So Young's modulus is also this spring constant, which is F over E times original length over extension, original length over cross-sectional area, original length over cross-sectional area. So if you can find a spring constant of a material and multiply it by the original length divided by its cross-sectional area, that gives us the Young modulus of the material. Now, to determine the Young modulus E of a wire, we can measure the unstretched length of the wire, that's the original length, unstretched or original length. L naught, then we stretch it using a weight or force, and then we measure the extension E, and we measure the cross-sectional area A. Remember, Young modulus is simply F times original length over, we were able to discover that Young modulus is force times original length over cross-sectional area times extension. Young modulus is force times original length over cross-sectional area times extension. So if we can find the unstretched or original length of the wire, and then we stretch it with a force or weight, and measure the extension produced, and measure the cross-sectional area, we can find the Young's modulus. Now this is how we carry out the experiment. This setup can be used. This is a G-clamp, and then we have the wire clamped onto a table or a bench using in between two wooden blocks like this, and that's the copper wire we want to measure its Young's modulus. Now the end of the copper wire is attached to a weight. We'll now be adjusting the weight. We start with maybe 100 kilograms or 100 grams, which will convert to kilograms, and increase it to 200 to 300 and so on. This is a pulley through which the string is passed, and then at the end of it is a weight or loads, which will help us to stretch the string, because the weight will stretch it as it applies a force by the pull of gravity. Then we have a ruler attached to the bench with a taper or a tape marker on wire used to measure the extension. Now there's a tape or a mark on the wire as the wire is being stretched and extended because as it is being stretched, it becomes longer. It carries the tape marker with it, so we can measure the extension. For instance, before we had a particular weight, we noted the position of the tape marker on the ruler, and then we provided a weight, and of course there will be an extension, which means this tape marker will move along the ruler. This was the original position before any weight was suspended. Now when you suspend a weight and then it is stretched, the tape marker will move because it is being elongated. So we take the measurement of the change in length between the original position of the tape marker and the new position after the weight is suspended. Assuming it was initially here, say at 25 centimeter initial position on the ruler, and then after we suspended the weight, it moved to 27 centimeter. Then it moved it to 27 centimeter. We can see that the extension is 27 minus 25, which is 2 centimeters. So that's the bench, that's a G-clamp, that's a wire, that's a tape marker on wire used to help measure the extension, and a pulley clamp to bench through which we pass the wire, and then the load or weights. So this is the procedure. You measure the diameter of the wire with a micrometer screw gauge or digital caliper or vernier caliper. We can take at least 3 readings and find an average. We measure different points on the wire. This is to help us reduce the uncertainty, because if you measure the diameter at one point on the wire and another diameter at another point on the wire and at another point of the wire, you calculate an average. That makes it more reliable and it will reduce the uncertainty. So measure the diameter of the wire with a micrometer screw gauge, take at least 3 readings and find an average. Set up the apparatus so that the wire is taut, properly tensioned. This wire will make sure it is stretched, as properly stretched or taut. That is when no mass is hanging. So no mass should be on the mass hanger. And then we measure the original length of the wire using a meter ruler and mark a reference point with a tape, preferably near the beginning of the scale. So we measure the original length from here to here, for instance, 25 centimeter from here to here, the original length or the unstretched length, and mark it. For instance, 25 centimeters. Then we record the initial reading on the ruler of the reference point, 25 centimeters, for instance. And then we begin to add the masses, add a 100-gram mass onto the mass hanger. We start with a 100-gram mass. When we hang a 100-gram mass, it will stretch, and then it will carry the tape marker along as it is being elongated. So from the 25 centimeter mark, it might move to 27 centimeter mark, for instance. From 25 centimeter mark, if it moves to 27 centimeter mark, we can see that the extension is 2 centimeters. We convert to units. Now read and record the new reading of the tape marker from the meter rule. Repeat this method by adding 100-gram mass for 6 times or 5 to 10 times and record a new scale reading from the meter rule. For instance, we can have readings like this: the mass in gram, the load, which we find by multiplying the mass. First of all, we change the mass to kilogram. To find the load, we have to change the mass to kilogram. which is mass in kg, times G, gravitational field strength, 9.81. You know, G itself is approximately 9.81 Newton per kilogram. So the load is simply as force or load is mass times G, the mass in kilograms, times G for each of them. And then of course the new marker reading after the masses are added. When 100 gram mass is added, we record the new marker reading. When 200 gram mass is added, we record the new marker reading, and so on, until we obtain at least 6 readings. 1, 2, 3, 4, 5, 6 readings. And then we can calculate the extension. For instance, if the unstretched length was, if the original length was 25 centimeter, and then when we added the 100 gram mass, it became 27 centimeter. That means the extension will be 27 minus 25. New length minus original length. Remember, extension is always new length minus original length. Extension is new length minus original length, or new length minus unstretched length. And all of that should be in SI units, so all must be in meter, just like the force is in Newton. So we have all these readings: the new length for 100 gram mass, the new length for 200 gram mass, 300 gram mass, and so on. With that, we can calculate the extension and convert to meter. And then we can plot the graph of the force against the extension, the force in Newton against extension in meter. We obtain a graph like this. With this graph, we can find the gradient, which is force over extension. By the way, this gradient, which is force over extension, gives us the spring constant. This is force over extension. This change in length is basically the extension, and that of course gives us the spring constant, K. Because force over extension, we've already established that force over extension is the spring constant, K. So we have that is from the slope. And then we can simply multiply the gradient by the original length, or the unstretched length, L0, by the cross-sectional area to find the Young modulus. Remember, we already said that the Young modulus is equal to F times original length over cross-sectional area times extension. Which we found to be F, or spring constant, times original length over cross-sectional area. Force over extension itself is spring constant. So the Young modulus is this spring constant which we got, the slope here, times original length on stretched length over the cross-sectional area, on stretched length over cross-sectional area. So we can use that So it's the gradient, the slope we found, times original length of our cross-sectional area. We use that to get the Young's modulus. In carrying out this experiment, there are certain systematic errors we need to avoid. Now, using a Venner scale, for instance, you can minimize the systematic error, and we must ensure that the wire is not extended beyond its elastic limit, because if it is extended beyond its elastic limit, it will be permanently deformed. And to reduce the risk, you need to remove the wire and remove the load. When you add a load, remove it and check, particularly towards the end of the experiment, when we have higher loads like 400, 500, 600. When those loads are added, remove the load and check that the wire returns to its original length before taking a new reading. Because if it doesn't return to its original length, it has passed the elastic region and is now in the plastic region, so it is permanently deformed and it does not obey Hooke's law again. So this formula does not stand. To avoid that, because that can produce a systematic error, remove the load and check that the wire returns to its original length before taking any new reading. That's one way to prevent systematic error. You can use a vernier caliper for more precise reading. That's another way. Now for random errors, which is usually from the user of the instrument, systematic error comes from the instrument itself, or the apparatus itself. Random error comes from the way the apparatus is used or the way the instrument is used. You need to avoid parallax error by reading at eye level when we are reading the marking on the ruler. These markings on the ruler should be read at eye level. For instance, when we are reading the marking on 25 centimeter mark or 27 or 29 and so on, it should be read at eye level. The level of the eye should be positioned exactly above the marking, vertically above it, so that the line of sight should make angle 90 degrees with the markings, the line of sight, and the ruler should be angle 90 degrees so that it will be to avoid parallax error. So we avoid parallax error by reading the marker when we are reading the marker on the ruler. We can also reduce random error by repeating the experiment for all the loads and finding an average. This will also help us to reduce the uncertainty. So for each load, we repeat the experiment and then find an average. For 100 gram mass, we take it twice, first reading, second reading, before we find the average and record it as the new marker reading. For 200 grams, we take it twice, first reading, second reading, find the average, which we record as our new marker reading before we calculate the extensions. Same for 300, first reading, second reading, the average as our new marker reading, and then we can now calculate the extension. All will help to reduce the random error. And then we can also reduce the uncertainty in the measurement of the cross-sectional area by measuring the diameter in several places along the wire. If this is the wire, for instance, we measure the diameter at one point, diameter at another point, diameter at another point in 3 different places, and calculate an average to get the diameter we're going to use to find the cross-sectional area. Remember, the cross-sectional area is pi r squared or pi d squared over 4. So for this diameter, we need to measure it in at least 2 or 3 places, several places, 3 places for instance. And then we calculate an average, and that's the average D we're going to use to calculate the cross-sectional area. That's about reducing systematic errors and random errors in this experiment. Systematic errors and random errors. And of course, for safety considerations, it's important to wear goggles throughout in case the wire snaps, to protect the eyes from any such accident. Wear safety goggles and make sure a cushioned soft surface is kept directly below the mass hanger in case it falls off. You know, this hanger where we are adding our masses at the base should have a proper cushioning, so that if the weight falls off, it doesn't constitute a serious hazard or a serious hurt to the user. All right, those are the safety considerations. Wear safety goggles at all times. Make sure a cushion or soft surface is kept directly below the mass hanger in case it falls off. We've looked at the systematic errors. To reduce it, we use a vernier caliper for more precise readings. And then we can get a more accurate value for the extension. Make sure the wire is not extended beyond its elastic limit. And to do this, to reduce the risk, you remove the load and check the wire returns to its original length before taking a new reading. And to reduce random errors, you need to avoid parallax error. By reading, it's not just enough to say avoid parallax error, you need to say how. The eye level should be directly on the graduation, such that the angle between the eye level and the markings will be at 90 degrees. So the eye level will be exactly directly on top or above the particular point you're reading. And then you repeat readings for each load and calculate an average, or for each measurement of the diameter of the cross-sectional, the diameter of the wire, and calculate an average before you can find the cross-sectional area. All of that is to reduce uncertainty. Okay. Please don't forget to like, subscribe, and comment. Thank you so much.
Welcome to Like Learning School, your premier online education platform. At Like Learning School, we are dedicated to helping students and learners unlock their full potential, providing them with the foundation, support, and guidance they need for academic excellence. Our platform caters to two main target audiences. Firstly, we work with school children of all ages, offering academic follow-up and accountability partnerships. Our seasoned tutors provide personalized attention to ensure students stay on track and reach their goals. Secondly, we support students and learners who are preparing for internal, external, entrance, or professional examinations. We offer comprehensive and well-structured support to help them achieve outstanding performance in their exams. Our robust virtual courses are designed to keep students engaged and motivated. With interactive videos showcasing our teaching sessions, students actively participate in the learning process, making education enjoyable and effective. But that's not all. We believe in personalized education. Our students have access to personalized tutorial sessions, whether online, physical, or hybrid, tailored to their unique learning needs. Join us at Like Learning School and experience a transformative education journey. Visit our website at www.likelearningschool.com or contact us at +234 808 509 5144 to learn more and get started today.